Hello there, and welcome to this peaceful journey through the cosmos. I'm so glad you found your way here tonight. Perhaps you've had a long day filled with earthly concerns, or maybe you're simply the kind of person who finds comfort in contemplating the vast mysteries that drift silently above us, rather than counting sheep. Either way, this evening's voyage is crafted especially for you. You have nothing to do now but rest. Let your shoulders drop gently, allow your breathing to slow naturally, and feel your body grow wonderfully light, as if the very gravity that holds you has softened into something gentler, more forgiving. Tonight, we won't simply be stargazing from our small world. Instead, we'll drift together through the infinite ocean of space itself, exploring the deepest mysteries that have puzzled astronomers and philosophers for generations. We'll encounter dark matter that flows like invisible rivers through the cosmos, witness the strange dance of black holes, and listen to the whispered secrets of distant galaxies spinning in the cosmic deep. You'll hear a phenomena so mysterious, they challenge everything we thought we knew about reality itself. Wormholes that might connect distant corners of the universe. Dark energy pushing galaxies apart in ways we still don't fully understand, and quantum fields that bubble with possibilities we can barely imagine. Some of what you discover tonight may spark quiet curiosity as you drift towards sleep, planting seeds of wonder that will bloom gently in your dreams. And if these calm explorations of cosmic mysteries help you unwind at the end of your day, consider subscribing to support more peaceful journeys like this one. It helps other restless souls find their way to these tranquil shores of discovery, one sleepy stargazer at a time. Now, let us begin our gentle drift through the universe's most beautiful enigmas. The enigma of dark matter in the vast expanse of the cosmos. There exists a substance so mysterious that it challenges our very understanding of reality. Dark matter, an invisible essence that comprises roughly 27% of everything that exists in the universe, remains completely hidden from our eyes and the most sophisticated instruments we have ever created. It can only be detected through its gentle gravitational influence on the visible matter around it. Like cosmic ghosts that flow silently through galaxies, through planets, and even through your body as you read these words, the discovery of dark matter began with a profound puzzle that emerged when astronomers studied the rotation of galaxies. They found that galaxies spin far too quickly to be held together by the gravity of their visible stars alone. According to our understanding of physics, these rapidly spinning stellar islands should have torn themselves apart long ago, flinging their stars into the void of intergalactic space. Yet there they are, stable and intact, spinning gracefully in the cosmic dance. Something invisible must be providing additional gravitational binding, wrapping each galaxy in an unseen halo that extends far beyond the furthest reaches of starlight. This dark matter cocoon cradles entire galactic families, ensuring they remain safely nestled together in gravitational embrace. The evidence for its existence comes not just from galaxy rotation curves, but from gravitational lensing effects, where the invisible matter bends light from distant objects, creating distorted images that reveal the presence of mass we cannot see. Computer simulations of cosmic evolution show that without dark matter, the large-scale structure of the universe as we know it simply could not have formed. The cosmic web of galaxies and galaxy clusters that stretches across billions of light years owes its existence to the gravitational scaffolding provided by this mysterious substance. Deep underground, in laboratories carved from solid rock and shielded from cosmic rays, scientists conduct one of the most ambitious treasure hunts in human history. They are searching for dark matter particles, hoping to catch these elusive cosmic visitors as they drift soundlessly through the Earth. These detection experiments are marvels of sensitivity, designed to register the incredibly faint interactions that might occur when a dark matter particle collides with an atomic nucleus in their carefully prepared targets. The challenge is immense, because dark matter particles may interact so weakly with ordinary matter that trillions pass through every square centimeter of space each second, leaving barely a whisper of their presence. The leading candidates for dark matter particles are exotic entities that exist beyond our current understanding of matter. They might be weakly interacting massive particles, or WIMPs that were created in the early universe, but have since become incredibly difficult to detect. Alternatively, dark matter might consist of axions, hypothetical particles so light and weakly interacting that they would be almost impossible to detect directly. Some theories even suggest that dark matter might be composed of primordial black holes, microscopic remnants from the early universe that formed from density fluctuations shortly after the Big Bang. What makes dark matter even more mysterious is that it appears to interact with itself and ordinary matter almost exclusively through gravity. This means that dark matter particles can pass through each other and through ordinary matter with virtually no resistance, creating a ghostly parallel universe of matter that occupies the same space as our familiar world, but remains largely invisible and intangible to us. The dark matter in our own galaxy forms a massive halo that our solar system moves through at approximately 230 kilometers per second. Yet we feel no resistance and detect no direct effects from this passage through the cosmic ghost medium. The implications of dark matter's existence extend far beyond academic curiosity. Understanding this mysterious component of our universe could revolutionize our comprehension of fundamental physics and cosmology. It might reveal new particles and forces that exist beyond the standard model of particle physics, opening entirely new realms of scientific exploration. The search for dark matter represents one of the most important quests in modern science, promising to unveil secrets about the nature of reality itself that have remained hidden since the beginning of time. The mystery of dark energy, even more enigmatic than the ghostly presence of dark matter, is a force that astronomers have come to call dark energy, which makes up approximately 68% of the universe and drives its accelerating expansion. This invisible energy permeates every corner of space, from the vast intergalactic voids to the space between atoms, gently pushing galaxies apart at an ever-increasing rate. It acts like the universe's own slow cosmic breath, inflating reality into something ever more vast and magnificent with each passing moment. The story of dark energy's discovery reads like a cosmic detective novel that began with astronomers studying distant supernovae, stellar explosions so bright they can briefly outshine entire galaxies. These cosmic lighthouses serve as standard candles, allowing scientists to measure distances across the universe with unprecedented precision. In the 1990s, two independent teams of astronomers were using these supernova observations to measure the deceleration of the universe's expansion, expecting to find that gravity was gradually slowing down the cosmic expansion that began with the Big Bang. What they discovered instead was so unexpected that it initially seemed impossible. The distant supernovae appeared dimmer than calculations had predicted, suggesting they were farther away than expected. This could only mean one thing that defied conventional wisdom. The expansion of the universe was not slowing down, but actually accelerating. Billions of years ago, the expansion had indeed been decelerating under gravity's influence, but then something fundamental changed. Around 5 billion years ago, dark energy began to dominate over matter and gravity, causing space itself to stretch faster and faster. This cosmic acceleration represents one of the most profound discoveries in the history of astronomy, fundamentally altering our understanding of the universe's fate and composition. The acceleration is gentle but relentless, increasing the distances between galaxy clusters by about 7 kilometers per second for every megaparsec of separation. While this might seem insignificant on human scales, over cosmic distances and time periods, it represents an enormous force that will ultimately determine the destiny of everything in existence. The true nature of dark energy remains one of the deepest puzzles in modern science, spawning numerous theories that attempt to explain this cosmic mystery. Some scientists propose that dark energy might be a property of empty space itself, a kind of inherent energy density that becomes more dominant as the universe expands and matter becomes more dilute. This concept, known as the cosmological constant, was actually first proposed by Einstein in his equations of general relativity, though he later considered it his greatest blunder when the expansion of the universe was first discovered. Other theories suggest that dark energy could be a dynamic field that changes over cosmic time, similar to the fields that drove cosmic inflation in the early universe. This hypothetical field, sometimes called quintessence, might vary in strength and could potentially even reverse its effects in the future. Some models propose that dark energy might be related to extra dimensions of space that we cannot directly perceive, or to modifications in the laws of gravity that become apparent only on the largest scales. The implications of dark energy's dominance are both fascinating and unsettling. As eons pass, this mysterious force may eventually overcome all other interactions, potentially leading to a scenario that cosmologists call the Big Rip. In this ultimate fate, dark energy's accelerating expansion could become so strong that it overcomes not just gravity, but also the electromagnetic and nuclear forces that hold atoms together. The universe would literally tear itself apart, dissolving every structure from galaxy clusters down to individual atoms in a final cosmic crescendo that would mark the end of physical reality as we know it. Black holes, cosmic doorways to the unknown scattered throughout the cosmos, are perhaps the universe's most enigmatic and awe-inspiring objects. Black holes, regions where matter becomes so compressed that the very fabric of space-time warps into shapes so extreme that not even light can escape their gravitational embrace. These mysterious entities represent the ultimate triumph of gravity over all other forces in nature, creating places where our understanding of physics breaks down and the universe keeps its deepest secrets, locked away in impenetrable darkness. Black holes form through one of the most violent processes in the universe, the collapse of massive stars at the end of their lives. When a star at least 8 times more massive than our Sun exhausts its nuclear fuel, it can no longer generate enough energy to support itself against its own crushing gravity. In a catastrophic implosion that occurs in less than a second, the star's core collapses to form a point of infinite density called a singularity, surrounded by a region of space-time so severely curved that it forms a one-way passage into the unknown. The boundary surrounding a black hole, known as the event horizon, represents perhaps the most profound frontier in the universe. This invisible spherical surface marks the point of no return, beyond which nothing can ever escape back to the outside universe. The size of this boundary depends on the black hole's mass, ranging from a few kilometers across for stellar mass black holes to billions of kilometers for the supermassive giants that lurk at the centers of galaxies. What makes the event horizon so mysterious is that it represents a fundamental limit to human knowledge. We can never observe what lies beyond it, or retrieve information about what falls into it. At the heart of nearly every galaxy lies a supermassive black hole, a gravitational monster containing millions or billions of times the mass of our Sun, yet occupying a space smaller than our solar system. These cosmic giants grew over billions of years by devouring gas, dust, and occasionally entire stars, gradually accumulating mass until they became the dominant gravitational force at their galaxy's center. We cannot see these behemoths directly, but we observe their influence through the spectacular dance of nearby stars that whip around them at tremendous speeds, tracing invisible orbits through the void like moths dancing around an unseen flame. The region immediately surrounding a supermassive black hole is one of the most extreme environments in the universe. Sometimes gas and dust spiral inward toward the event horizon, forming a swirling accretion disk that heats to temperatures of millions of degrees through friction and gravitational compression. This superheated material flares with brilliant X-rays and gamma rays in its final moments, before vanishing forever beyond the event horizon, creating some of the brightest and most energetic phenomena in the cosmos. These active galactic nuclei can outshine all the stars in their host galaxy combined, broadcasting their existence across billions of light-years of space. What lies beyond the event horizon remains one of science's greatest mysteries and most profound questions. According to Einstein's general relativity, matter falling into a black hole would be stretched and compressed by tidal forces until it reaches the central singularity, where density becomes infinite and space-time curvature becomes undefined. Yet this classical description breaks down when quantum effects are considered, leading to paradoxes that challenge our most fundamental understanding of reality. The information paradox represents one of the deepest puzzles in modern physics. When matter falls into a black hole, it seems to disappear completely, potentially taking with it all the quantum information that defined its properties. This creates a fundamental conflict, because quantum mechanics insists that information cannot be destroyed, only transformed or hidden. The resolution of this paradox may require a complete revolution in our understanding of space-time, gravity, and information itself. Stephen Hawking's discovery that black holes slowly evaporate through quantum radiation adds another layer of mystery to these cosmic enigmas. According to quantum field theory, virtual particle pairs constantly appear near the event horizon, and occasionally one particle from a pair falls into the black hole while its partner escapes as Hawking radiation. This means that even the most massive black holes in the universe are gradually shrinking, returning their energy to space over timescales so vast they dwarf the current age of the universe by countless orders of magnitude. The puzzle of cosmic inflation. In the first fraction of a second after the Big Bang, the universe underwent the most extraordinary transformation in its entire history, a period of exponential expansion called cosmic inflation that stretched space itself faster than the speed of light, growing from smaller than a subatomic particle to the size of a grapefruit in an impossibly brief moment that lasted less than a trillionth of a trillionth of a trillionth of a second. This mind-bending episode represents one of the most crucial yet mysterious chapters in cosmic evolution, solving fundamental puzzles about the nature of our universe, while simultaneously raising even deeper questions about the fabric of reality itself. The concept of cosmic inflation emerged from attempts to solve several perplexing problems with the standard Big Bang theory. Astronomers had long wondered why the universe appears so remarkably uniform in temperature and structure, across vast distances that should never have been able to communicate with each other, given the finite speed of light and the age of the universe. They also puzzled over why the geometry of space appears to be perfectly flat, balanced precisely on the knife's edge between eternal expansion and eventual collapse. Additionally, theoretical predictions suggested that the early universe should have been filled with exotic relics, like magnetic monopoles, yet none have ever been observed. Cosmic inflation elegantly resolves these mysteries through a process so rapid and dramatic that it defies ordinary imagination. During this inflationary epoch, space itself expanded exponentially, driven by a mysterious energy field that permeated the entire universe. This expansion was not the movement of matter through space, but rather the stretching of space itself, which allowed it to exceed the speed of light without violating the principles of relativity. As space expanded, any irregularities or exotic particles that existed before inflation were diluted to undetectable levels, while quantum fluctuations in the inflating field were stretched to cosmic scales, providing the seeds for all future structure formation. The driving force behind this incredible expansion is proposed to be a quantum field called the inflaton field, an entity unlike any other field known to physics. This field possessed the remarkable property that its energy density remained nearly constant as space expanded exponentially, continuously fueling the inflationary process like a cosmic engine that never ran out of fuel. The inflaton field existed in a state of false vacuum, a temporary energy configuration that was stable enough to drive inflation, but ultimately unstable, destined to decay into a lower energy state. When inflation finally ended, the inflaton field underwent a phase transition, releasing its enormous stored energy in a process called reheating. This energy conversion created the hot, dense soup of particles and radiation that filled the early universe, essentially generating all the matter and energy that would eventually form stars, galaxies, planets, and everything we observe today. In a very real sense, cosmic inflation was responsible for creating the raw materials of existence from the quantum vacuum itself, transforming empty space into a universe teeming with possibilities. The implications of cosmic inflation extend far beyond our own universe and venture into realms that challenge our most basic assumptions about reality. If inflation occurred once in our cosmic neighborhood, the same physical processes that drove it may be occurring constantly throughout a vast cosmic landscape, creating what cosmologists call eternal inflation. In this scenario, our observable universe represents just one tiny bubble in an infinite sea of expanding realities, each potentially governed by different physical laws and constants. This concept of the multiverse suggests that countless other universes might exist beyond our cosmic horizon, each representing a different outcome of the inflationary process. Some of these universes might have physical constants that prevent the formation of atoms, while others might have properties that allow for entirely different forms of matter and energy. The anthropic principle suggests that we observe a universe compatible with our existence simply because we exist to observe it, while countless other universes with incompatible properties remain forever beyond our reach. Recent observations of the cosmic microwave background radiation have provided compelling evidence for the inflationary theory, revealing patterns of temperature fluctuations that match precisely the predictions of inflation models. These observations represent fossil evidence of quantum fluctuations that occurred during the inflationary epoch, stretched to cosmic scales and preserved in the afterglow of the Big Bang. Yet many fundamental questions remain unanswered, including what caused inflation to begin, what determined when it ended, and whether the process continues in other regions of space-time. Quantum fields and virtual particles, even in the emptiest regions of space, billions of light years away from any stars or galaxies, where the density of matter approaches zero and the temperature hovers just above absolute zero. The universe hums quietly with an invisible symphony of quantum activity that never ceases. What we intuitively think of as empty space, a perfect void devoid of all substance and energy, is actually filled with quantum fields, invisible energy fields, that permeate every corner of reality and give rise to virtual particles that pop into existence for brief moments before vanishing back into the quantum vacuum like cosmic ghosts dancing at the edge of existence. These quantum fields represent one of the most fundamental aspects of reality according to our current understanding of physics, and every type of particle known to science, from electrons and photons to quarks and neutrinos, corresponds to excitations in its own quantum field that extends throughout all of space and time. The electron field fills every cubic centimeter of the universe, as do the photon field, the quark fields, and all the other quantum fields that together form the invisible substrate upon which physical reality is built. When we observe a particle, we are actually witnessing a localized excitation in its corresponding field, like a wave rippling across the surface of an infinite ocean. The quantum vacuum, far from being empty, seethes with constant activity, as virtual particles emerge spontaneously from the energy inherent in the fields themselves. These virtual particles come in pairs, typically consisting of a particle and its antiparticle, appearing spontaneously from the quantum foam and existing for only tiny fractions of a second before annihilating each other and disappearing back into the vacuum. This process occurs everywhere and at all times, with virtual particles of every type constantly materializing and dematerializing in a cosmic dance that operates far below the threshold of direct observation. Though these virtual particles might seem like mere theoretical constructs with no real physical significance, they have measurable effects on the behavior of atoms, light, and even the structure of space-time itself. The Casimir effect demonstrates that virtual particles can exert real forces, as two parallel metal plates placed very close together in vacuum will experience a slight attraction due to the difference in virtual particle density between the plates and the surrounding space. Virtual particles also contribute to the slight shifts in atomic energy levels, known as the Lamb shift, providing precise experimental confirmation of their existence. The influence of virtual particles extends to some of the most extreme environments in the universe, particularly in the vicinity of black holes, where the intense gravitational fields create conditions that can separate virtual particle pairs before they have a chance to annihilate. Near a black hole's event horizon, something remarkable happens to these ephemeral particle pairs. Sometimes one particle from a pair falls into the black hole, while its partner escapes into space, becoming a real particle in the process. This mechanism, predicted by Stephen Hawking, causes black holes to slowly evaporate through a process called Hawking radiation, gradually returning their mass energy to the universe in the form of thermal radiation. This black hole evaporation process reveals the deep connections between quantum mechanics, thermodynamics, and gravity in ways that continue to puzzle physicists. The temperature of Hawking radiation is inversely related to the black hole's mass, meaning that smaller black holes radiate more energetically than larger ones. For stellar mass black holes, this radiation is incredibly faint and cold, with temperatures far below that of the cosmic microwave background, making it practically undetectable. However, for hypothetical microscopic black holes, the Hawking radiation would be intense enough to cause rapid evaporation, in brilliant flashes of energy. The quantum vacuum and its virtual particles also play a crucial role in the evolution of the universe itself. During cosmic inflation, quantum fluctuations in the inflaton field were stretched to astronomical scales, providing the seeds for all large-scale structure formation. These quantum fluctuations, amplified by the exponential expansion of space, created the tiny density variations that eventually grew under gravity's influence to form galaxies, stars, and planets. In this sense, the quantum vacuum and its perpetual activity were directly responsible for the cosmic architecture we observe today. Modern quantum field theory suggests that the energy density of the quantum vacuum itself might contribute to the cosmological constant, potentially explaining the mysterious dark energy that drives the accelerating expansion of the universe. However, calculations of vacuum energy density yield results that are many orders of magnitude larger than observed, creating what physicists call the cosmological constant problem, one of the most significant discrepancies between theory and observation in all of science. The cosmic web and large-scale structure, on the largest scales imaginable, spanning billions of light-years across the observable universe, space reveals an intricate and beautiful architecture known as the cosmic web, a vast network of filaments and voids that resembles a three-dimensional spider's web stretching across the entire cosmos. This magnificent structure represents the grandest organizational pattern in nature, connecting every galaxy and galaxy cluster through invisible bridges of dark matter and threading together the fundamental building blocks of the universe into a coherent, interconnected tapestry that took billions of years to weave. Dark matter forms the invisible scaffolding of this cosmic architecture, providing the gravitational framework upon which ordinary matter can collect and condense into the galaxies we observe today. The cosmic web emerges naturally from the gravitational collapse of matter in an expanding universe, beginning with tiny quantum fluctuations in the early cosmos that were amplified during cosmic inflation and subsequently grew under the patient influence of gravity over billions of years. Computer simulations of cosmic evolution show that dark matter naturally organizes itself into a web-like structure, with dense filaments connecting massive nodes where galaxy clusters form, while vast regions between the filaments remain nearly empty. These cosmic filaments, some stretching for hundreds of millions of light-years, contain most of the ordinary matter in the universe, though much of it remains invisible in the form of hot gas that fills the space between galaxies. Galaxies trace out the densest parts of these filaments like glowing Christmas lights strung along invisible cosmic highways, marking the locations where dark matter concentrations were strong enough to trigger star formation. The filaments themselves are not static structures, but dynamic systems, where matter continues to flow along the gravitational channels carved out by dark matter, streaming toward the massive galaxy clusters that mark the intersections of the cosmic web. Between these filaments lie enormous cosmic voids, regions of space so empty they contain almost no galaxies at all and represent some of the most pristine and undisturbed environments in the known universe. These voids can span hundreds of millions of light-years across, containing less than 1/10 the average density of matter found elsewhere in the cosmos. Within their quiet depths, space is remarkably empty, with typical densities far below the cosmic average and very few bright galaxies to illuminate the darkness. The largest of these voids are so immense that light takes hundreds of millions of years to cross from one side to the other, creating regions where an observer would see very few galaxies in any direction. The cosmic web continues to evolve, today as gravity draws matter along its filaments toward the intersections, where galaxy clusters form, creating some of the most massive gravitationally bound structures in the universe. These clusters can contain thousands of galaxies bound together by the gravity of dark matter halos that contain trillions of times the mass of our Sun. The process of cluster formation represents an ongoing cosmic construction project that has been underway for billions of years, with smaller structures merging to form larger ones in a hierarchical process that will continue far into the future. Galaxies stream along these invisible highways at hundreds of kilometers per second, guided by the gentle but persistent pull of dark matter's gravitational currents toward ever larger structures. This cosmic flow creates a dynamic system where matter is constantly in motion, following paths determined by the gravitational landscape carved out by the cosmic web. Our own Milky Way galaxy participates in this grand cosmic dance, moving through space as part of the local group of galaxies, which itself is falling toward the massive Virgo cluster along one of the cosmic web's filaments. The study of large-scale structure provides crucial insights into the composition and evolution of the universe, offering a unique laboratory for testing our understanding of dark matter, dark energy, and the fundamental physics that govern cosmic evolution. By mapping the distribution of galaxies and measuring their motions, astronomers can trace the underlying dark matter distribution and study how structure formation has proceeded over cosmic time. These observations have revealed that approximately 5% of the universe consists of ordinary matter, 27% is dark matter, and 68% is dark energy, fundamentally changing our understanding of what the universe is made of. The cosmic web also serves as a fossil record of the early universe, preserving information about the conditions that existed shortly after the Big Bang. The patterns we observe in galaxy distribution today reflect the quantum fluctuations that existed during cosmic inflation, stretched to enormous scales and amplified by billions of years of gravitational growth. By studying the statistical properties of the cosmic web, scientists can learn about the physics of the very early universe and test theories about cosmic inflation, dark matter, and the fundamental nature of space and time itself. The arrow of time and entropy, one of the universe's most fundamental and perplexing mysteries, is why time seems to flow in only one direction, from past to future, when the basic laws of physics are largely symmetric in time and contain no inherent preference for forward or backward temporal flow. This puzzle is intimately connected to entropy, the measure of disorder in a system, and the tendency for all systems to become more disordered over time, and to the strange and remarkable fact that our universe began in an incredibly low entropy state that defies statistical expectations and continues to challenge our understanding of cosmic origins. The concept of entropy emerged from thermodynamics in the 19th century, originally describing the irreversible flow of heat from hot to cold objects and the tendency for energy to become less available for useful work over time. However, entropy's implications extend far beyond simple heat engines to encompass the fundamental nature of time itself. In any isolated system, entropy can only increase or remain constant, never decrease, a principle known as the second law of thermodynamics that appears to be one of the most universal and inviolable laws of nature. In the early moments after the Big Bang, matter and energy were distributed with remarkable uniformity across the entire observable universe, representing a state of extraordinarily low entropy compared to the highly clustered and structured universe we see today. This initial smoothness, revealed by observations of the cosmic microwave background radiation, shows temperature variations of only 1 part in 100,000 across the sky. Such uniformity represents an incredibly special and improbable initial condition, requiring an explanation for why the universe began in such an organized state rather than in the chaotic, high-entropy configuration that probability would suggest. As billions of years passed and gravity pulled matter together into the first stars and galaxies, the universe underwent a fascinating paradox of organization and disorganization occurring simultaneously. Locally, matter became more organized as it collapsed under gravity to form increasingly complex structures. Gas clouds condensed into stars, stars formed galaxies, galaxies clustered together, and eventually planets formed, where life could emerge and create even more intricate patterns of organization. Yet globally, the universe became more disordered as gravitational collapse released enormous amounts of energy in the form of heat and radiation, increasing the total entropy of the cosmos. This ongoing increase in entropy provides time with its directional arrow, fundamentally distinguishing past from future and explaining some of the most basic asymmetries we observe in everyday life. We remember the past but not the future, because memory formation requires energy expenditure that increases entropy, creating records of past events while the future remains uncertain and undetermined. Broken eggs don't spontaneously reassemble, not because the laws of physics forbid it, but because the probability of all the scattered pieces randomly coming together in exactly the right configuration is astronomically small. Heat flows from warm to cold objects because there are vastly more ways for energy to be distributed randomly than concentrated in organized forms. The thermodynamic arrow of time also explains why we observe cause preceding effect rather than the reverse, why mixing occurs spontaneously while unmixing does not, and why aging progresses in one direction toward increasing disorder at the cellular level. Every biological process, from metabolism to reproduction to neural activity, involves irreversible increases in entropy that contribute to the overall arrow of time. Even the expansion of the universe itself can be viewed as an entropy-increasing process as space grows larger and matter becomes more dilute. Yet, fundamental questions remain about why the universe began in such an improbably ordered state and whether this initial low entropy requires explanation through new physics or represents a brute fact about cosmic initial conditions. Some cosmologists propose that cosmic inflation might explain the universe's initial low entropy by stretching a small, high-entropy region to enormous size, effectively diluting irregularities and creating apparent uniformity. Others suggest that the arrow of time might be connected to the expansion of the universe itself, with time's direction determined by the direction of cosmic expansion. The relationship between entropy and information adds another layer of complexity to the mystery of time's arrow. In modern physics, entropy can be understood as a measure of missing information about a system's microscopic configuration. When we say a gas has high entropy, we mean that there are many possible arrangements of its molecules that would appear identical at the macroscopic level. This connection between entropy and information has profound implications for understanding black holes, quantum mechanics, and the fundamental nature of physical reality. Some theories propose that time's arrow might not be universal, but could vary in different regions of space, or under extreme conditions, near black holes or during cosmic inflation. The possibility that time's direction could be reversed, or that multiple time dimensions might exist, represents one of the most speculative frontiers in theoretical physics, challenging our most basic assumptions about causality and the nature of temporal flow. The mystery of entropy and time's arrow ultimately connects to the deepest questions about why anything exists at all, and why the universe has the particular properties we observe, rather than existing in a state of maximum entropy and thermal equilibrium. The fact that we live in an era of cosmic history, when stars are still forming, galaxies are still evolving, and complexity can still increase, suggests that we exist during a special epoch in the universe's thermal evolution. Billions of years after the Big Bang, but trillions of years before the final heat death, when entropy reaches its maximum and time's arrow may lose its meaning. Parallel universes and the multiverse. The concept that our universe might be just one of countless others has undergone a remarkable transformation from the realm of science fiction into serious scientific consideration, representing one of the most profound shifts in cosmological thinking since the discovery that our galaxy is not the entire universe. Several independent theories in modern physics suggest that parallel universes might exist, each representing different ways the quantum possibilities of reality could unfold, different solutions to the equations that govern cosmic evolution, or different regions of an infinite cosmic landscape where physical laws and constants might vary in ways that challenge our most basic assumptions about the uniqueness of our cosmic home. The many worlds interpretation of quantum mechanics presents perhaps the most radical vision of parallel universes, suggesting that every quantum measurement causes reality to branch into multiple parallel worlds, each representing a different possible outcome of the quantum event. In this interpretation, developed by physicist Hugh Everett, the wave function that describes all possible quantum states never actually collapses, but continues to evolve deterministically, creating an ever-branching tree of parallel realities. Every time a quantum measurement occurs, from the decay of a radioactive atom to the firing of a neuron in your brain, reality splits into multiple parallel branches, each equally real, but forever separated from the others. This interpretation suggests that there could be versions of you making different choices in countless parallel universes, all equally real, but occupying different branches of the universal wave function. In some nearby branches, you might have made slightly different decisions today, while in more distant branches, history might have unfolded completely differently, with different outcomes for everything from personal relationships to world wars to the evolution of life on Earth. These parallel selves would be as real and conscious as you are, but they would exist in separate quantum branches, with no possibility of communication or interaction. Cosmic inflation provides another pathway to parallel universes through a process called eternal inflation, where the same quantum field that drove the exponential expansion of our universe continues to operate in other regions of space, generating an infinite number of pocket universes like bubbles in an endless cosmic foam. Each of these pocket universes could have different physical constants, different particle physics, and even different numbers of spatial dimensions, creating a vast multiverse where our observable universe represents just one small bubble in an infinite sea of expanding realities. In some of these parallel universes, the fundamental constants of nature might be slightly different, leading to radically different cosmic evolution. Universes where the strong nuclear force is slightly weaker might never form atomic nuclei, while universes where gravity is stronger might collapse back on themselves before stars have time to form. Some universes might have different particle physics entirely, with exotic forms of matter and energy that don't exist in our cosmic neighborhood, while others might have additional spatial dimensions that allow for entirely different forms of geometry and physics. String theory, the attempt to unify quantum mechanics with general relativity, suggests yet another form of multiverse through its concept of the landscape of possible vacuum states. In string theory, the fundamental constants of nature are not fixed, but depend on which vacuum state the universe happens to occupy in a multidimensional space of possibilities. The landscape might contain an enormous number of possible vacuum states, perhaps 10 to 500 or more, each corresponding to a universe with different physics, different particles, and different laws of nature. This string landscape multiverse would contain universes so alien that we can barely imagine them, with different forces governing matter, different particles carrying energy and information, and possibly different logical structures underlying physical law. Some regions of this landscape might support complexity and life, while vast regions might be sterile and empty, unable to support the organized structures necessary for biological evolution or conscious observation. The anthropic principle provides a potential explanation for why we observe the particular combination of physical constants and laws that exist in our universe. If the multiverse contains regions with every possible combination of physical parameters, then we necessarily observe a region compatible with our existence simply because we exist to observe it. Universes with different constants might be equally real but would remain unobserved because they could not support the complex chemistry necessary for life and consciousness to emerge. The implications of the multiverse concept extend beyond physics into philosophy, raising profound questions about the nature of existence, probability, and meaning. If infinite parallel universes exist, then every possible event that can occur does occur somewhere in the multiverse, making concepts like probability and uniqueness fundamentally different from our ordinary understanding. The question of whether science can ever provide evidence for the existence of parallel universes remains hotly debated, with some arguing that untestable theories about other universes lie beyond the boundaries of empirical science. Recent developments in cosmology and quantum physics continue to refine our understanding of how parallel universes might exist and interact. Some theories propose that different universes might occasionally collide or influence each other through quantum tunneling effects, potentially leaving observable signatures in our cosmic microwave background or in the large-scale structure of the universe. Others suggest that the multiverse might be finite rather than infinite, with a vast but countable number of parallel realities rather than truly unlimited possibilities. The information paradox and quantum gravity, when matter falls into a black hole, it seems to disappear completely from our universe, potentially taking with it all the quantum information that defined its properties, creating one of the most profound paradoxes in modern physics that strikes at the heart of our understanding of information, causality, and the fundamental nature of physical reality itself. This creates a fundamental conflict because quantum mechanics, one of the most successful theories in physics, insists that information cannot be destroyed, but can only be transformed, hidden or redistributed in ways that preserve the total information content of any physical system. The black hole information paradox emerged from Stephen Hawking's groundbreaking discovery that black holes emit thermal radiation through quantum effects near their event horizons, causing them to slowly evaporate over enormous periods of time. As virtual particle pairs appear near the event horizon, occasionally one particle falls into the black hole, while its partner escapes as Hawking radiation. This process continues until the black hole completely evaporates, leaving behind only thermal radiation that appears to contain no information about the matter that originally formed the black hole or fell into it during its lifetime. This scenario violates a fundamental principle of quantum mechanics known as unitarity, which requires that information about any quantum system must be preserved throughout its evolution, even if that information becomes highly scrambled and practically impossible to retrieve. The principle of unitarity underlies the predictive power of quantum mechanics and ensures that the probabilities of all possible outcomes of any quantum process sum to unity. If information can be destroyed by falling into black holes, then quantum mechanics would be fundamentally incomplete or incorrect, requiring a revolutionary revision of our understanding of physical law. The resolution of this paradox has spawned numerous theoretical proposals that push the boundaries of our understanding of space, time, gravity, and information. Some scientists propose that information falling into a black hole becomes encoded on its event horizon through a holographic principle, where the three-dimensional interior of a black hole represents a kind of holographic projection of information stored on its two-dimensional surface. This holographic encoding would preserve all the information that falls into the black hole, but in a form so scrambled and distributed that it would be practically impossible to decode. The holographic principle suggests that the maximum amount of information that can be contained in any region of space is proportional to the area of its boundary rather than its volume, implying that our three-dimensional experience of reality might itself be a holographic projection of information encoded on a distant two-dimensional surface. This concept has profound implications for understanding not just black holes, but the fundamental nature of space, time, and physical reality itself, suggesting that the familiar three-dimensional world we experience might be an emergent property of more fundamental two-dimensional physics. Another proposed resolution involves the concept of black hole complementarity, which suggests that information falling into a black hole can appear to be simultaneously destroyed from the perspective of an outside observer and preserved from the perspective of someone falling into the black hole. This resolution requires that no single observer can witness both the apparent destruction and preservation of information, maintaining consistency within each reference frame while avoiding the paradox through the relative nature of information and observation. The search for a theory of quantum gravity represents one of physics' greatest challenges and most ambitious goals, attempting to unify Einstein's general relativity, which describes gravity and the large-scale structure of space-time, with quantum mechanics, which governs the behavior of matter and energy on the smallest scales. String theory, loop quantum gravity, causal dynamical triangulation, and other approaches each attempt to describe what happens at the Planck scale, where quantum effects become important for gravity, and where space and time themselves might break down into something more fundamental. String theory proposes that all fundamental particles are actually tiny vibrating strings existing in multiple dimensions beyond the three spatial dimensions we experience directly. In this framework, gravity emerges from the vibrations of closed strings, while matter and force particles arise from open strings attached to higher dimensional surfaces called branes. String theory naturally incorporates quantum mechanics and general relativity, but requires additional spatial dimensions and predicts a vast landscape of possible vacuum states, each corresponding to different physics and different values of fundamental constants. Loop quantum gravity takes a different approach by proposing that space and time are not continuous but are composed of discrete quantum building blocks at the Planck scale. In this theory, space itself has a granular structure, with tiny loops and nodes forming the fundamental fabric of reality. This discreteness eliminates many of the infinities that plague attempts to quantize gravity and suggests that black hole singularities might be replaced by quantum bounces that could preserve information. Through black hole evaporation, the resolution of the information paradox and the development of quantum gravity might require revolutionary new concepts that go beyond our current understanding of space, time, causality, and information. Some theories propose that information might be preserved through wormhole connections between black holes and distant regions of space-time, while others suggest that the very concept of information might need to be redefined in a quantum gravitational context. The ultimate answer to these questions will likely transform our understanding of reality at the most fundamental level, potentially revealing that space-time, matter, and information are all emergent properties of a deeper, more fundamental layer of physical reality that we are only beginning to glimpse. The ultimate fate of everything, as we peer into the far future with the eyes of modern cosmology, we encounter scenarios for the ultimate fate of our universe that are each more sublime and mysterious than earthly imagination might conjure, stretching across timescales so vast that the entire history of human civilization represents less than a fleeting instant in the cosmic story that lies ahead. Based on current observations of dark energy's accelerating expansion and our understanding of stellar evolution, particle physics, and thermodynamics, the most likely scenario is that the universe will continue expanding forever, driven by dark energy's relentless and ever-strengthening push that will eventually overcome every other force in nature. In this cosmological future, known as the heat-death scenario, the universe will undergo a gradual transformation from the vibrant, star-filled cosmos we know today into something almost unimaginably different. Over the next several trillion years, stars will continue to form from the remaining gas and dust in galaxies, but this star formation will gradually slow and eventually cease entirely as the raw materials become exhausted or dispersed beyond the reach of gravity. The most massive stars will burn through their fuel quickly and explode as supernovae, while smaller stars like our Sun will expand into red giants before shedding their outer layers and fading into white dwarf stars that will cool slowly over hundreds of billions of years. As this stellar twilight progresses, galaxies themselves will begin to drift apart as dark energy's expansion carries them beyond the cosmic horizon, making them invisible to each other and effectively isolating each galaxy in its own expanding bubble of space. Eventually, even within individual galaxies, the expansion will overcome the gravitational binding between stars, causing stellar systems to dissociate and leaving individual stars wandering alone through the growing emptiness. The universe will become an increasingly cold, dark, and empty place, illuminated only by the fading glow of dying stars and the occasional flash of matter falling into black holes. After approximately 10-14 years, even the longest-lived red dwarf stars will have exhausted their nuclear fuel and faded to cold, dark cinders. The universe will enter what cosmologists call the degenerate era, dominated by the slowly cooling remnants of dead stars, white dwarfs, neutron stars, and black holes of various sizes. During this phase, which could last for 1037 years or more, the primary source of energy will come from the occasional collision between these stellar remnants and from the gradual decay of complex atoms, through quantum tunneling effects that allow protons to overcome the energy barriers that normally keep atomic nuclei stable. The black holes that formed from collapsed stars and grew by accreting matter over billions of years will become the dominant structures in this future universe, ranging from stellar mass black holes containing a few times the mass of our Sun to supermassive black holes that grew to contain billions of solar masses. These gravitational monsters will continue to slowly evaporate through Hawking radiation, with smaller black holes radiating away their mass energy more quickly than larger ones. A black hole with the mass of our Sun would take approximately 10,067 years to completely evaporate, while the most massive black holes in the universe would require 10,100 years or more to disappear entirely. Even protons, the fundamental building blocks of atomic nuclei that have remained stable throughout cosmic history, might eventually decay through processes predicted by grand unified theories of particle physics. If protons do indeed have a finite lifetime, as some theories suggest, then after approximately 1034 years, all atomic matter will have disintegrated, leaving behind only electrons, photons, neutrinos, and other stable particles drifting through an ever-expanding void. This would mark the beginning of the photon era, when electromagnetic radiation becomes the dominant form of energy in the universe. Yet even in this seemingly bleak future, quantum mechanics suggests possibilities that transform despair into wonder. Given infinite time, the quantum vacuum will continue to fluctuate, occasionally producing virtual particles that become real through random chance. These quantum fluctuations could, over unimaginably vast periods, spontaneously assemble into complex structures through pure statistical accident. Random quantum fluctuations might occasionally create patterns of matter and energy that resemble stars, planets, or even living organisms, though these structures would exist for only brief moments before dissolving back into the quantum chaos from which they emerged. The concept of Poincare recurrence suggests that in a finite region of space, given infinite time, quantum fluctuations will eventually recreate any possible configuration of matter and energy, including exact duplicates of every moment in cosmic history. Entire civilizations might spontaneously form from quantum vacuum fluctuations, experience brief but complete histories, and then dissolve back into nothingness, only to be recreated again in endless cycles of emergence and dissolution, played out across timescales that dwarf even the vast ages of stellar evolution and black hole evaporation. Some theories propose alternative fates for the universe that could interrupt this slow slide toward maximum entropy. If dark energy is not truly constant, but instead represents a dynamic field that changes over cosmic time, it might eventually weaken or even reverse its effects, potentially causing the universe's expansion to decelerate and eventually collapse in a big crunch that would mirror the Big Bang in reverse. Other theories suggest that quantum effects in the far future might trigger a new phase transition that completely transforms the nature of space, time, and matter. The cyclic universe models propose that our cosmos might be just one phase in an eternal cycle of expansion and contraction, with each cycle lasting hundreds of billions of years before collapsing and rebounding into a new Big Bang. In this scenario, the apparent heat death of our universe would be followed by a new period of cosmic inflation and the birth of new stars, galaxies, and perhaps new forms of life and consciousness entirely different from anything that has existed in our cosmic epoch. Perhaps most intriguingly, some theories suggest that consciousness itself might play a fundamental role in the far future evolution of the universe. If intelligence can survive the heat death through technological transcendence or by encoding itself in the quantum structure of space-time itself, then conscious observers might be able to influence the evolution of reality through quantum measurement effects, potentially steering the universe toward outcomes that preserve meaning and purpose even in the face of maximum entropy. These mysteries remind us how much remains unknown, how many questions float unanswered in the cosmic deep. Dark energy pushes galaxies apart for reasons we cannot fully fathom. Black holes hide information in ways that challenge our deepest theories. The quantum vacuum bubbles with virtual particles that appear and vanish, like cosmic thoughts. Yet there is profound beauty in these mysteries, a gentle wonder that connects us to something far greater than ourselves. As you rest tonight, remember that you are made of the same quantum fields that permeate empty space, composed of atoms forged in stellar cores billions of years ago, participating in the same cosmic story that began with the Big Bang and continues to unfold in ways we are only beginning to understand. The universe keeps its deepest secrets wrapped in silence and starlight, in the invisible scaffolding of dark matter and the patient expansion driven by dark energy. And somewhere in that vast tapestry of mystery and wonder, you find your place, a conscious observer capable of contemplating the very cosmos that gave birth to you. Sleep well tonight, knowing that you are connected to these cosmic mysteries in the most intimate way possible. The quantum fields that fill empty space flow through your body. The expansion of the universe carries you forward through time. The same physical laws that govern distant galaxies also guide the beating of your heart. Dream gently of dark matter rivers and parallel worlds, of quantum possibilities and cosmic horizons stretching beyond imagination. Let the peaceful mysteries of the universe carry you into rest, wrapped softly in the infinite patient embrace of space and time. Good night, fellow traveler in the cosmic deep. May your dreams be filled with starlight and wonder.